This is Bob Capetta from the University of Illinois at Chicago, and this lesson is on sequences. And they can be defined using this notation. A sub n is 3n plus 1. And the n's we're allowed to use are counting numbers, whole numbers. We cannot use real numbers like fractions or irrational numbers. So I can start with an n of 0 here. That's where we often start. And you can see what a sub 0 would be. Plugging an n of 0 in, a sub 0 is 3 times 0 plus 1, or 1. A sub 1, plugging a 1 in, 3 times 1 plus 1, 3 plus 1 is 4. A sub 2, 3 times 2 plus 1, 7. A sub 3, plugging in an n of 3, 3 times 3 plus 1, 10. And this can go on as long as you want it to go on. So I've just got a few of them here for this sequence, 1, 4, 7, 10, 13, 16. You'll notice they all differ by 3. That characterizes an arithmetic sequence. This is an example of an arithmetic sequence. Now, as n goes to infinity, what happens to this sequence? Well, you can see it grows without bound. It's monotone increasing. It continues to grow. So we have an increasing function that grows without bound. The limit's not going to exist. So the limit as n goes to infinity of a sub n does not exist. I corrected the slide. Limit as n goes to infinity of a sub n does not exist. Let's look at another example. B sub n is 7 times 1/2 to the n power. Starting with an n of 0, 7 times a half to the 0, 7 times 1 is 7. So b sub 0 is 7. B sub 1, now n is 1. 7 times a half to the first is 7 halves. N is 2, 7 times a half squared. 7 times a quarter, 7 quarters. B sub 3, 7 times a half to the third. 7 times an eighth, 7 eighths. B sub 4, plugging 4 in for n, 7 times a half to the fourth, 7 times the 16th, 7 sixteenths. And B sub 5, 7 times a half to the fifth, 7 times 1 over 32, 7 32nds. This goes on forever. So for this sequence, I have a few of the elements of that sequence. It's a geometric sequence because the ratio between any two consecutive elements of this sequence is constant. It's always a half. To get from 7 to 7 halves, you multiply it by a half. 7 halves to 7 fourths, multiply by a half. 7 fourths to 7 eighths, multiply by a half. If there is a common ratio between two consecutive terms, then we have a geometric sequence. Now, the question is, what happens as n goes to infinity here? So I want to know the limit as n goes to infinity of this sequence. The limit as n goes to infinity of 7 times 1/2 to the nth power. In our first case, the limit as n went to infinity of a sub n did not exist. What will happen here? Well, I can pull the 7 out. It's a constant. It can come out in front of the limit operator. So 1/2 to the n is 1 to the n over 2 to the n, but 1 to the n is just 1. So we get 7 times the limit as n goes to infinity of 1 over 2 to the n. Well, if n gets large, 2 to the n gets very large. 1 over a number getting increasingly large will give us a limit value of 0. So the limit as n goes to infinity of b sub n this time does equal 0. Our numbers get smaller and smaller and smaller and smaller, which is apparent here as we look at the elements of the sequence. Each number is half as large as the one before. So if you keep taking half of what you have, the limiting process is going to have to yield 0. Our next example is the sequence a sub n equals 1 minus 3 over n to the nth power. So a sub 1, 1 minus 3 over 1 to the first. That's incorrect. It's fixed. 1 minus 3 over 1 is negative 2 to the first power is negative 2. 1 minus 3 over 2 to the second power, 1 minus 3 halves is negative 1/2 squared is a quarter. A sub 3, 1 minus 3 over 3 to the third power. Well, that's 1 minus 1, 0 to the third power is 0. A sub 4, 1 minus 3 quarters to the fourth power. 1/4 to the fourth power, 1 over 256. A sub 5, 1 minus 3/5 to the fifth power, 2/5 to the fifth power, or 32 over 31/25. Does this sequence tend to 0? These numbers appear to be getting smaller, but we need to do some analysis to convince ourselves of that. So let's examine the limit as n goes to infinity of 1 minus 3 over n to the nth power. I want to call it L. So the limit as n goes to infinity of a sub n, I'm just going to substitute L to make it a little easier for me to work with. I'm also going to change the n's to x's, and let me explain why. N implies integers. When we're working with sequences, we're working off of whole numbers, counting numbers, integers. But if I'm working with a function over real numbers, and x usually implies real numbers, then I can use L'Hopital's rule. It doesn't make any sense to take a derivative of a function only defined on integers. So I usually replace n with x to clarify that I'm looking at the behavior over the real numbers, and however it works for the real numbers will also work over the natural numbers. So the first thing I'm going to do is I'm going to take the natural log of both sides. So the log of L is the log of that limit. And then we can switch the limit and the log thanks to continuity. And then we know our rule from algebra: if you have a log of a function to the x power, we can bring the x in front of the log. Now don't bring the x in front of the limit, because of course x is changing. So we get natural log of L is the limit as x goes to infinity of x times the natural log of 1 minus 3 over x. We haven't used L'Hopital yet, but I'm going to rewrite x as divided by 1 over x. So notice as x goes to infinity, the bottom 1 over a large number goes to 0. The top 3 over a large number goes to 0. 1 minus 0 goes to 1, but log of 1 of course is 0. So we have a 0 over 0 case. Therefore, it is fair for us to use L'Hopital's rule. And to remind you, to use L'Hopital's rule, take the derivative of the top and the derivative of the bottom, and then take the limit. So there we go, derivative of the top, derivative of the bottom. The derivative of the log of something, 1 over the something times the derivative of the inside. The derivative of 1 is 0. I'll need the derivative of negative 3 over x. The derivative of 1 over x, x to the negative 1 over x squared. So there we have the derivative of the log of something, 1 over the something times the derivative of the something. But the derivative of 1 is 0. The derivative of negative 3x to the negative 1 is 3x to the negative 2, so 3 over x squared divided by negative 1 over x squared. Now I've got division of fractions. Let's multiply by the reciprocal. So instead of dividing by negative 1 over x squared, let's multiply by x squared over negative 1. The x squareds cancel. 3 divided by negative 1 becomes negative 3, as a constant can come in front of the limit operator. So we have negative 3, 3 over negative 1, negative 3 times the limit as x goes to infinity of 1 over 1 minus 3 over x. As x gets very large, 3 over a large number goes to 0. 1 minus 0 goes to 1. We have 1 over 1 here. Negative 3 times 1 over 1, of course, is going to give us negative 3. So we have the natural log of L equals negative 3. The base of the natural log is e. So e to the negative 3 power equals L. Now what was L? Remember, L was the limit as n goes to infinity of a sub n, which was the limit as n goes to infinity of 1 minus 3 over n to the n. And we get a relatively small number, but not 0. We get e to the negative 3 in this case. Our next example is what we call a recursive function. So what happens next is dependent on what happened before. So the next element is twice the previous element minus 5. That's how we can make sense of this. But I have to seed it. I have to have a starting point. So we're going to say b sub 0 is 3. That's the first element in this recursive function. Now I've got to go with various numbers for n. So I want to get b sub 1, I will need n to equal 0. If n equals 0, b sub 0 plus 1. b sub 1 will be 2b sub 0 minus 5. We know b sub 0 is 3. And again, n equals 0. b sub 0 plus 1 is 2b sub 0 minus 5. So that's b sub 1 is 2 times b sub 0, 2 times 3 minus 5. 6 minus 5 is 1. So now we know b1 is 1. We have the next element of our sequence. Now to find b sub 2, I'm going to need to have n equals 1, because if n equals 1, b1 plus 1 would be b sub 2. n equals 1, b sub 1 plus 1 is 2 times b sub 1, since n is 1, minus 5. 2 times what would be b sub 1? b sub 1 was 1. 2 times 1 minus 5. 2 minus 5 is negative 3. So we have b sub 2 here is negative 3 for this element of our recursive function. To get b sub 3, I need n to be 2. b sub n plus 2, b sub 2 plus 1 is 2b sub 2 minus 5. b sub 2 plus 1, n is 2, is 2b sub 2, n is 2 minus 5. b sub 2 plus 1, b sub 3, is 2 times b sub 2. 2 times negative 3 minus 5. Negative 6 minus 5 is negative 11. So b sub 3 is negative 11. And let's do one more. We'll go to n equals 3. If we go to n equals 3, that will give us b3 plus 1. That will give us b4 is 2b3 minus 5. Again, n is 3. b sub 3 plus 1 is 2b sub 3 minus 5. b sub 4 is 2 times b sub 3. 2 times negative 11 minus 5. Negative 22 minus 5 is negative 27. And again, there's our b4 is negative 27. This is a recursive sequence. When you have the next elements be dependent on what comes previously, we call that a recursive sequence. Here's another one we're going to look at, another recursive sequence. F sub n plus 2 is f sub n plus 1 plus f sub n. So 2 later is the one previous plus the one before that. I need 2 seeds. We're going to take f sub 0 is 0 and f sub 1 is 1. I'm going to start with an n of 0. F sub 0 plus 2. F sub 2 should be f sub 0 plus 1. F sub 1 plus f sub 0. So f sub 2 should be f sub 1 plus f sub 0, 1 plus 0. Let's write that down again. Plugging 0 in for n, f sub 0 plus 2 is f sub 0 plus 1 plus f sub 0. So f sub 2 is f sub 1 plus f sub 0. F sub 1 is 1. F sub 0 is 0. 1 plus 0 is 1. That is our f sub 2. So we know f sub 2 is 1. To get f sub 3, I need n to equal 1. f1 plus 2 f3 is f2 plus f1. f2 is 1. f1 is 1. 1 plus 1 is 2. So we have f sub 3 is 2. Notice it's the 2 previous. 1 plus 1 gives us 2. To get f sub 4, we need n equals 2. f2 plus 2 f4 is f3 plus f2. f3 is 2. f2 is 1. 2 plus 1 is 3. Again, notice f sub 4 is the 2 previous added. 2 plus 1. Similarly, n is 3. f3 plus 2 is f3 plus 1 plus f sub 3. f5 is f4 plus f3. f4 is 3. f3 is 2. 3 plus 2 is 5. And similarly, to get n equals 4, f6 is f5 plus f4, which is 8. This is a famous sequence, maybe the most famous sequence. It's a Fibonacci sequence from Leonardo of Pisa. There's one last thing I want to talk about in this lesson, and that's this notion of sequences of partial sums. This is a series because it is the sum of something as n goes from 0 to infinity. It is an infinite series. And one of our important questions will be whether or not an infinite series converges. But to build up the concept, we have to think about sequences of partial sums. What do we mean by that? If I stop, I'm not going to go all the way to infinity. I'm going to stop at n. So if I stop at 0, n goes from 0 to 0, all I have is the first term, a sub 0. My sum, if I stop at 1, that's the 0th term plus the first term. If I stop at 2 elements, that's the 0th plus the first plus the second. Similarly for the third, 0th plus first plus second plus third. And the nth term, we stop at the nth. 0th, first, second, third, fourth, fifth, sixth, seventh, go all the way out to the nth term. That's how we start with a series and reconsider it as a sequence of partial sums. Now, the series will converge when the sequence of partial sums also converges. So we're going to look at 7 times 1/2 to the n. We looked at it as a sequence earlier in this lesson. Let's look at it as a series this time. So the sum, as n goes from 0 to infinity, of 7 times 1/2 to the n. So the first term is a0. If n is 0, 7 times a half to the 0 is just 7. That is the first term. That is also the first sum. If I add the 0th and the first element, I get 7 plus 7 halves, which is 21 halves. S sub 2 is the 0th, first and second. 7 plus 7 halves. If n is 2, a half squared is 4, 7 fourths. We add those three and we get that number. If s is 3, we take our partial sums up to the third element. 0th plus first plus second plus third. If n is 3, a half to the third is 8. That's 7/8. So 7 plus 7 halves plus 7 fourths plus 7/8. Looking at all these things, 7, 21 halves, 49 fourths, 105/8. We could do some analysis to express that as a function of n. But I just want to make sure that we're clear on what this means. This series converges if that limit exists. That's what it means for a series to converge, is that the sequence of partial sums also converges. And that will conclude this lesson.